Okay, so we're going to put in f of x is y1, g of x is y2, similar to what we did yesterday, and we're going to be looking at the characteristics between these two graphs. Yesterday we were looking at an exponential in comparison to a power function. Today we're looking at both exponential, but what's the difference between the two? What's the difference just by looking at, you guys can't even see it, just by looking at f of x and g of x algebraically? What can you tell is the difference between the two? What do you mean opposites? We're reciprocals, which means one is going to be what type of graph and the other. In terms of, how do we word that in terms of exponentially? If we've got something, there's two different kinds of exponential functions that we can have.
One's going to be positive, one's going to be negative.
One's going to be
power, decreasing and increasing.
Give me other words for that. Those are, you're all on it.
Growth and decay.
Growth and decay. I've got one that's a growth, one that is a decay. F of x would be which one of those? Growth. And g of x is decay. Perfect. How do I know that? How do I know that difference? B here is greater than 1. B here is less than 1. The other class was using the word fraction because g of x has a fraction. And that's really, yes, that's true for this particular situation, but that's not something that we can say all the time, because what if it was 3 halves? It's a fraction, but that's greater than 1, and so it'd still be gross. So we can't just look at it in terms of it being a fraction. All right, so the domain, once you have those graphs up, and that's what they would look like, does it look like there's any restriction to my domain on either one of them? No. So similar to what we saw yesterday, our domain is going to be all real numbers, and the range also is going to be the same for both that we saw yesterday. There's nothing that's below the x-axis. Both the graphs lie above the x-axis, but they both contain a what that limits them from 0 being part of the, they both have horizontal asymptotes. Okay, they both have horizontal asymptotes, so therefore neither one of them can have 0 inclusive into their range. Do they both look continuous? Yes, because I could draw both of them without lifting up my pencil. The boundedness, similar to what we talked about yesterday, they're both bounded below because there's no points that lie below either one of those functions. Do either one of them have a max or a minimum? Nope, so there's no local extrema on either one of them. Do they have an asymptote or asymptotes? A horizontal at y equals 0. So far, this has been pretty ho-hum. Seriously, this is it. But when we get to the last two characteristics, this is when they split apart, and it starts to distinguish the growth from the decay. So a growth function, even without looking at the graph, would you assume a growth to be an increasing or decreasing function? Increasing. And so if you would take your pencil to draw that, you would start at that horizontal asymptote and go up. And that's exactly what is happening with your increasing function. I try to do that backwards so you guys can see it from there. Decreasing, would you assume it to be increasing or decreasing? I'm sorry. Decay. I just gave you the answer. The decay function, would you assume it to be increasing or decreasing? Perfect. It is a decreasing function again. If you were to draw that with a pencil, your graph would be going in the downward direction as you were drawing that. Perfect. Okay? My in behavior, again, is where we're going to separate a growth function from a decay function. So the limit of the function as x approaches negative infinity is something. Limit of the function as x approaches positive infinity is going to be something. So I look at my graph, and my growth, my f of x, is here to the right-hand side, starting at the left, going to the right. So as far as in behavior goes, I start at the origin, and as x goes to negative infinity, what is the behavior of the graph? It approaches 0 because that's the side of the horizontal asymptote for my growth. So this approaches 0. Then on the other side, as I start at infinity, excuse me, that would be the origin. As I start at the origin and the x value moves toward infinity, the graph is approaching positive infinity. Good job. Okay? Then I'm going to do the same thing for my g of x. But this time, my decay starts off on the left-hand side, but as x goes to negative infinity, what's my graph doing? It's going to positive infinity. These are just flip-flop, which should make sense. And then as it goes to positive infinity off to the right, it is approaching, that's where the horizontal asymptote is for the decay function, is off over here. Questions on the characteristics and similarities and differences between those two graphs? Okay? Pretty straightforward as we are going through that, except for my increasing, decreasing, and in behavior on that. Okay? This next part that we're going to transition into is really where I'm going to be looking and asking and checking to make sure that you're understanding how an exponential function is applied. And a lot of times with exponential functions, we see an application in population situations. And I was flipping through trying to update some of our problems that we have, and I was flipping through your textbook, and it's really kind of comical because, number one, math doesn't change, all right, as far as it is the same as it was years ago. The way in which we teach it can change, but the actual situations that we have in math stay the same. And so the textbooks, as long as it's, an author may put a little flair here or there, as far as the textbook goes, but it's pretty much the same. And so we particularly like this textbook as far as the methodology through it and the sequence that it goes through. So it hasn't changed in quite a while. And so I look at this problem, and it talks about the city of Columbus, Ohio from 1990. You guys weren't even born in 1990. And I'm thinking, oh, that's pretty recent. But you guys weren't even born. And so I found it funny, the number of situations in which you guys were like, seriously? This is like so long ago. But anyway, so I apologize on that, but it is what it is. It'll still get the point across, and I guess that's the main thing we're looking at here. So here we go. So the city of Columbus, Ohio grew from 1990 at a population of 632,910 to the year 2000, where it was 711,265. So we are assuming the growth is exponential. You on your own cannot assume exponential unless it's stated, and this is what I mean by that. Otherwise, if we have 2 points, we're looking at a line. We're looking at a linear function rather than an exponential. So we're assuming the growth is exponential. We want to know, when is the population of Columbus going to surpass 800,000? This is something that's used for the city planners, using a model in growth. What's really interesting that just hit me, on the news last night, night before, they're stating that Quincy has not grown. Oh, I want to throw out a year, but I don't know exactly. But in last, 70, 30 years. I mean, it's the same population, 40,633 or whatever it was, stayed the same. So that, we may even be in type of a decay type or stagnant, exponential function rather than a growth exponential function. So interesting on that. So the thing that we need to understand, that when it comes to population, I think the things that, as you look at this, you see the date 1990. And if we go and understand what is the basic function that we learned yesterday of an exponential function. Y equals what? A times b to the x. That's my generic function. Keep that in mind, because the only two variables that I need to supplement in, I need to find values for, are which ones? A and B. A is my, what did A stand for?
Initial value.
Is my initial value, where things start, the beginning. And what's B? Base growth factor. or decay factor, okay? So A is my initial value and B is my growth or decay factor, all right? So I look through this and I see date and I see a number. I don't see initial value. I don't see a growth factor. But let's take a step back. When you have a set of data that's given to you, like Columbus, Ohio, it wasn't founded in 1990. So you can't look at that as in 1990 and all the years prior to that. This is a set of data that's saying that we're going to study starting at 1990. 1990 is my starting point, and then I'm going to move forward. So if I would use, and this is what I would suggest and recommend, like if you have a situation like this, which you will, set up your own XY chart. Set up your own XY chart. And I know my initial value is my initial value when X is what?
0.
When X is 0, I know I have found my initial value. When X is 0 is my starting point. So on this set of data, where is my starting point? Let me rephrase that. When is my starting point? 1990. So right here, that is my X value is 1990. But I'm going to plug that in as 0 because that's my starting point. So at 1990, what was the population? 632,910. So that is my X value, which is then my initial value, which is A. And I'm putting that in at 0 because that's when they started the data for this particular study. All right, so then if 1990 is when the study started, how many years passed to when they calculated the population again? So 10 years passed, and they found the population to be?
711,265.
Perfect. Okay? And I think with population, when we have word problems like this, we want to use the real number 1990, and we want to use the number 2000. And I don't mean to say it's irrelevant. That's not the case at all. It's very, very relevant. But we don't use it in terms of the year. We use it in terms of a starting point and then how many years have passed that starting point. Okay? So given that, we are now going to work it just like we had the problem at the very end of the class yesterday. Okay? So what am I going to substitute in for y?
711,000.
Perfect. 711, 265. And what is my starting value?
5.
How about 632,
Oh,
910? Because when x is 0, that's going to be my initial value. I don't know my base. I don't know my growth factor. But what's my x value? 10. Okay, so take a second to make sure you see where all those numbers came from. Okay? What's my first step in solving this? Divide by 632, blah, blah, blah. Because I want to isolate my base. I want to get base by itself. And this is where we were talking about yesterday, how to find a higher level root, higher number root on our calculators. And so to get rid of b to the 10, what root am I taking? The 10th root, you know, just like you do all the time. So if you can do that in your head, go for it. If you can't, then I'm sorry, you probably need to just kind of freshen up on that a little bit. So the 10th root of 1 point, and honestly, guys, I'm not exactly sure why I took that out to the 10,000s. Normally it's to the hundreds, okay? But obviously in a situation like this, the further out you take a number, the more accurate it will become. If I'm going to be very specific on it, I will let you know for sure how far out to take it. So b becomes, what's the 10th root of 1.1238? All right? So now I want to write out the new exponential function pertaining specifically to this set of data. So I'll write that. F of x equals my starting value, my initial value of 632,910. My base, which is my growth factor, because I can tell that it is a growth from 1990 to the year 2000. The population did grow, so I could know that even before knowing that my base is greater than 1, and then raised to the x value. So we want to know, when is the population going to surpass 800,000? Given this equation, give me some ideas on how I can solve for that.
We could plug it in for B.
Plug what in for what?
The 800,000 for y to solve for x.
Okay, how do I solve for an exponent though yet? We haven't quite learned what you kind of did last year. How else can I do it?
Graph it.
Graph it. That'd be one way. You could graph it, you could look at your table, and if you're really not in the mood for graphing today, I still haven't heard another way. I know that 10 years have passed to get to me 7-11. Put in 15. Put in whatever, and just do a guess and check. There's another way in which we could do that. All right, so choose your method. Go for it. Tell me, when approximately will this surpass 800,000? Yes.
And we still plug in 800,000 for Y? Or we don't?
No, because in the next section is where we're going to learn how to do that and solve for. That's with using logarithms.
Can I check the population?
Yeah,
I wanna
yes.
see if it's accurate.
Yeah, see how accurate it is? Well, this is probably accurate, but in 20 years, because now that we're living it,
It's pretty close. Wait. Yeah. It is pretty close.
is it?
It's about $4,000 off in 2016.
So how many years is it going to take to get to surpass 800,000 to be find? About 21? 20, 21?
So that'd make it 2011.
Okay. And that's what Blake was doing. He was kind of checking to see, since we're past that, we can live to see if that's true or not. So
2011, it was about 800,000 really.
there it is. Okay. So it was fairly accurate, not exact, but again, like I said, city planners use exponential models such as this in order to kind of gauge, as far as roads and infrastructure and that kind of stuff, on what do they need as far as their city growth is concerned.
Surprisingly stable city.
That is, in assuming a stable economy, assuming stable growth, yes.
Is there a way to like write a formula for abnormal exponential functions? Like say it's like exponential up to a certain point and then it
And then, yes,
deviates?
not in this class.
Wait, why do you
But
know
yeah,
that
they
it's
can do that.
2011?
What, honey?
Why do you know that it's 2011?
Because it's in about 21 years, and whether it was through graphing, through the table, or through guessing and checking, and then take 1990 plus 21.
Oh, okay.
Yep, and you get that.
Yeah, so it's pretty much exactly right. Because I imagine that was 2011, like the first of the year when they measured it.
Correct. Correct. Okay, so we're going to move on to